normally from the University of Arizona, but this year at the Institute for Advanced Study in Princeton. And the title is on his first slide, Doubly Periodic Monopoles and Exploded Geometry. Sergey?
Thank you, Jan. Thank you for the invitation. So I hope to describe certain type of modular spaces today and convince you that they're interesting. And the way you can view them or which realization you prefer much depends on your background. So today I'll introduce them as modular spaces of monopoles, but they also have many other reincarnations, which I'll mention. So first, what's a monopole? Given a three-dimensional Riemannian manifold M, a monopole is two pieces of data. It's a Hermitian bundle E of M and a pair, a connection, and the Higgs field phi. So the Higgs field is simply endomorphism of E. And they have to satisfy two conditions. First, the Bogomolny equation, which, well, given an endomorphism, you can compute its exterior differential, covariant exterior differential, that gives you one form in local trivialization. And we insist on the curvature 2 form being Hodge dual, which starts Hodge star, to d phi. In every case, to have a good problem, you have to impose appropriate boundary conditions, and I'll specify this in a minute. In usual parlance, when M is R3 with a flat metric, these are solutions are referred as monopoles. When the space has one periodic direction, so if M is R2 crosses 1, again with flat metric, then it is with Euclidean metric inherited from the universal covering space, that is a periodic monopole. And if there are two directions periodic, so if your space is R cross a circle, then it's doubly periodic monopole.
And there is a three-periodic option, yeah? Like,
yes, indeed. There is triply periodic monopole, and I'll mention those as well. So not to say such long expression all the time, doubly periodic monopole, you can call them monopole walls or monowalls. And the reason for this is that any such solution, you can always view from the point of view of the covering space. And in the covering space, if you look far enough, the doubly periodic configuration looks like a wall. And for short, you can call them monowall. So next, we want to formulate a good moduli problem. So given a solution, star, you can view it as living in the sea of solutions, or in the larger set of solutions. Then a monopole in R3 was singled out by saying that you look at all solutions with L2 curvature, finite L2 norm of curvature. And for monopoles in R3, this was sufficient to give good moduli space. We'll have to rethink this condition a little bit, because as we'll discover, for periodic or doubly periodic monopoles, there will be no solution satisfying this condition. So instead, what we do is we look at, if you like, all gauge equivalence classes of solutions. That's this blue rectangle represents. And then given a particular solution, you can ask for its for a set of solutions which can be reached by L2 deformations of that. Namely, you can vary the connection, you can vary the endomorphism, and you insist on the variations being L2. So then the whole space is now being separated into this substrata, which are reachable by L2 deformations from a given solution. And that's what we call a moduli space. So being slicing the whole space into monopole space, the set of those is parameterized by what we call parameters. So if you fix parameters, then all solutions with those parameters form a moduli space. So in a sense, what we'll discuss today is a twofold problem. We want to specify parameters, then we want to describe the phase space of those possible parameters. And for each set of parameters, there is its own moduli space, and we want to understand the geometry of that space. So indeed, it is important to fix these parameters correctly. They will be encoded in the boundary conditions. And if it is done correctly, then indeed, the boundary conditions capture the moduli space. Now, you might not be interested in monopoles at all, but you might be interested in the same moduli space for entirely different reasons. For example, recently there was quite a bit of interest in supersymmetric gauge theories with 8 real supercharges. Now, all of these, I claim, are related to monopoles. So, for example, monopoles in R3. Sorry?
No, I mean, you're just explaining, so that's my question, in what way? Are they isomorphic? Or?
Exactly. So if you look at moduli space of monopoles in R3, as originally was pointed out by Seiberg and Witten, or I guess by Chalmers, Hanani, and Witten, the moduli space of monopoles, which is purely a classical problem, is isometric to the Coulomb branch of n equal 4 three-dimensional gauge theories. If you look at periodic monopoles, then moduli spaces of those give you Coulomb branches of n equal to 4-dimensional theories with a periodic direction. You can see that these two problems are related by varying the radius of the circle and sending it to infinity. Indeed, moduli space of periodic monopoles can degenerate into moduli space of monopoles in R3. And similarly, there's a relation between these two gauge theories. But to relate these two, you have to be shrinking the circle of the 4-dimensional theory to reduce it to 3-dimensional media. Similarly, doubly periodic monopoles that we'll discuss today are related to n equal 1 5-dimensional gauge theory with 2 periodic directions. So this theory on R3 cross T2.
And what about 3 periodics? You do not have n anymore because like
that's right. Therefore, I mean, I'm not making a claim.
But either
all right. Yes, I have special slide for you. So
okay. Yes,
let's come back to this question, and I'll show you what they're related to. They're related to moduli spaces of instantons, in fact. They have yet another incarnation, since this is an M theory seminar. These spaces appear as moduli spaces of branes. From the point of view of string theory, you can describe each of these as moduli spaces of particular brane configuration in string theory. Or equivalently, there is another description of these, in particularly in the last case that we'll discuss today, as moduli spaces which describe dynamics of M5 brane on Riemann surface across a circle. Also, whenever these spaces have lowest dimension, namely real dimension 4, they are good sources of self-dual gravitational instantons. So these are solutions of Einstein equations with Riemann curvature, two form being self-dual. Another way of describing this, these are hyperkahler manifolds of the lowest dimension. And these fall in different classes depending on how fast the volume grows. The volume of a large ball grows with radius, and these are called ALF, ALG, and ALH. And again, it's this type of space that will be focused on today. Traditionally, if you wanted to construct monopoles, in principle, constructing a monopole involves solving nonlinear PDE in 3 dimensions. But there was a neat construction found by Nam based on ADHM construction. And that involves some kind of nonlinear Fourier transform. And in case of monopoles, Nam transform produces an integrable system of equations which are, well, they depend only on one variable. So these are just ODEs. So indeed, this was a very efficient way of constructing monopoles. In case of periodic monopoles, Nam transform produces PDEs, namely Hitchin equations in 2 dimensions. And in the case we'll be describing today, if you try to construct a ADHM description of a doubly periodic monopole, you will end up with another doubly periodic monopole. So in a sense, in our case, we have to face the problem head on. We don't have a simplification resulting from non-transform or some type of ADHM construction.
What are slings in this?
That's right. So in case of monopoles or instantons on ILF spaces, norm data had to be augmented by various boundary conditions, and these were arranged into bows. So often moduli spaces of monopoles fall into this class of bow varieties. So similarly, periodic monopoles, as we showed in our work with Kapustin, correspond to a particular case of Hitchin system. But there are other ALG spaces which can be described in terms of Hitchin spaces which are combined in a certain way, and this total combination is what I call a sling. So in both of these cases, there is substantial simplification by performing the norm transform. But in the case we discussed today, there isn't. So we really have to study it by some other means. Okay. Any other questions?
So the slings, they are not kind of linear algebra data like in the bow variety case.
Well, in the bow variety case, also, if you're interested in the metric, that does involve solving norm equations on intervals.
Mm-hmm.
So similarly here, now it involves solving Hitchin equations with appropriate relations between residues and so forth. So if you're interested in modular space of this supersymmetric gauge theories, for example, then if you compactify them further to 2 dimensions, then if you want to describe their vacua, you are not so much interested in M itself, but vacua of this reduced theory is given by L2 cohomology of this modular space. So this is a good motivation for studying not just the space itself, but studying its L2 cohomology. And similarly, as I already mentioned, these modular spaces come in different kinds, and L2 cohomology is very sensitive to asymptotic metric, in particular to volume growth and so forth. So from this point of view, if you're after L2 cohomology of the spaces, there's 2 questions you have to answer. One is you need to describe the asymptotic geometry of M, understand what kind of ends these manifolds have. And second, it would be good to find a natural compactification. By natural, I mean, we want to find the compactification such that its ordinary L2 cohomology produces L2 cohomology of M.
Sergey, may I ask you just, first of all, M seminar doesn't mean M theory seminar, so this is a mathematical seminar. And so my question is mathematical then. So your M is hyperkahler always?
Yes.
Okay, good. Is it algebraic typically? So it's a question rather about
L2. Space, it's hard to tell if it's algebraic or not. The answer to this question will depend on your choice of a complex structure.
Yeah, I understand.
Right, so it might be algebraic in one complex structure, not algebraic in others.
Yeah, but it's rather a question about L2 cohomology, because if you have a non-compact space, which is kind of algebraic nature, you can try to work algebra geometrically. L2 is a complicated, yeah. So
Indeed, exactly. So it would be very hard to capture it purely algebra geometrically, but in some sense, today I hope to give some partial answer to exactly algebraic approach to this problem.
Okay.
So I think there is an algebraic way of formulating the right compactification, of course, in one special complex structure, well, one of 2 special complex structures in this case. So let's return to this question a little bit later. Indeed, I'll try to describe this this situation algebraically later. But as Jan just pointed out, indeed, L2 cohomology is a subtle question, and it's often hard to capture algebraically. Okay, so these are the two questions I aim to address today. So since we cannot use any ADHM type construction in this case head-on, let us get some sense for what monopole moduli spaces are. So first, we'll give coordinates to various directions in our space. So our space is R cross a circle, so R cross a torus. And the coordinates will be X is the non-compact coordinate along R, phi is the vertical coordinate along torus, and theta is the meridian coordinate around the torus. And first, as a warm-up, let's look at an abelian situation. So if our structure group is abelian, then the equation itself, ADHM equation, becomes linear. So in some local trivialization, your curvature is just exterior derivative of, is a differential of some one form. And so that has to be equal to star d phi. From this equation, it immediately follows that phi is a harmonic function. And well, there are only so many harmonic functions on R cross S1, which behave decently at infinity. In other words, if we insist that our function doesn't grow exponentially, then it can be at most linear. So this phi, in abelian case, has to look like this: qx plus m. Now, because gradient of phi is equal to q is interpreted as curvature, you can see that indeed this q is simply the turn number of the resulting bundle on the torus, so q has to be integer. And the subleading term m can be anything you wish. So it's a real number. And indeed, in this case, there are no moduli. Once you fix q and m at infinity, that is it. So you can think of q, for example, as a magnetic field, and in this case, this magnetic field dA will be just constant. It's constant curvature amongst fraction. So in general, to formulate a good problem for a general case, we will insist that at infinity, our Higgs field phi, well, there's a trivialization at infinity in which the Higgs field phi has this diagonal form. So the bundle splits into eigenbundles of phi, and on each subbundle, phi has this abelian form. From this, you can see that the connection also has to have very specific structure, namely the curvature on each bundle is specified by this q, and it might have some subleading terms which appear in the asymptotic behavior of the eigenvalues of the holonomy around theta and phi directions. So at infinity, we fix the following values. We fix q, which we will argue in a second has to be rational in this case, m, which is a real value, and two chi's, which really specify points each specifies a point in a unit circle. Next, you might choose not to allow this, but the story, as you will see, becomes much more symmetric if you allow direct singularities. So in R cross a torus, you mark some points, and some of them are marked as positive points, some as negative. And at these points, you allow phi to behave as 1 over R. And for now, we will allow only one of the eigenvalues of phi to behave this way. So our monopole is really defined on the complement of these points.
Okay, just to follow your notation, so plus and minus are plus and minus infinity along the only non-compact direction, yeah? This R.
In a case, plus and minus signify whether indeed we go in positive or negative direction along x. And in B case, they specify positive or negative charge of Dirac singularity. So whether eigenvalue of phi, or rather of I phi, goes to plus infinity or minus infinity.
Mm-hmm.
So in this definition, I only allow Dirac singularities of charge +1 or -1. And indeed, just this setup allows to capture most of spaces of this type. And as I will argue at the end of the talk, there will be two spaces which escape us, and they can be captured by allowing some singularities of high charge. Okay, any other questions? So the statement here is that if you specify these boundary conditions, then you get a moduli space. That is, two solutions satisfying these boundary conditions are connected by L2 definitions. Next, as I mentioned, the charges Q at positive or negative infinity have to be rational. The reason is purely topological. The bundle E at positive or negative infinity splits into eigenbundles of Higgs field. And then if you want to compute the Chern number of that bundle, then, well, it's integral of trace of curvature restricted to that subbundle, J subbundle. That's given in terms of gradient of phi. And because phi has this block structure, it will be given simply by gradient of phi, which is Q, and trace will give you another factor, which is rank of that bundle. So that product has to be integer. As a result, Q has to be a rational number. And the denominator has, well, can have some multiplicity R. As it turns out, asking a question about how just the dimension of the moduli space of this object is nicely formulated in terms of Newton polygon. And also, Newton polygon is a very convenient way of packaging this whole data with boundary conditions that I just mentioned. And here is how it is constructed. Think of the cylinder with coordinates x and theta. And then, as you go to plus infinity, you can draw these lines with slopes equal to corresponding charges. All these lines signify the growth rate of eigenvalues of Higgs field at plus infinity. Similarly for minus infinity. And then for every negative Dirac singularity that you mark, draw a ray pointing down. And for every positive one, draw a ray pointing up. So now, for each such line, since it has rational slope, there is another rational line which is perpendicular to it. I just wrote out its coordinates here. So think of these vectors. Each of these charges may have some multiplicity. So beta has to do with denominator of the slope, and R might be extra multiplicity. There might be few of these eigenvalues. So in that case, what we'll do next is we'll draw a polygon with integer vertices whose sides correspond exactly to these vectors. So each vector on the right-hand side, for example, is a vector with integer beginning and end on integer lattice, and it's a vector perpendicular to the line given by the charge.
I'm a bit confused. So in R3 you have two periodic directions. So I thought that these lines, it's kind of one-dimensional affine foliation with transversal complex structure, and your Dirac singularities should be singularities of some holomorphic bundle on the transversal curve. But the transversal curve seems to be elliptic, and you draw the cylinder, so I'm a bit confused. Probably your direction.
So we'll get to the curve in a second. What's important here is that we kept only the slopes in this theory, okay, only the rate of growth. And in fact, this Newton polygon will be exactly the Newton polygon of the polynomial which defines the curve that you mentioned. That's why I call it Newton polygon. But at the moment, the prescription is quite simple. You take the charges, which are rational numbers. You take multiplicities of those charges. And then for each charge, you draw a vector, which is perpendicular to that slope. And all these vectors, if you combine them, will assemble into a nice polygon. And indeed, the curve that you mentioned will explain why it is a polygon and why there is this consistent condition.
No, actually, my question was rather about the space where this curve, probably you're talking about spectral curve, when this curve is located. And it should be probably C star cross C star, like C star square, instead of the cotangent bundle.
You're anticipating the next slide. That's right. You're anticipating the next slide here, right? Exactly. So if you write Bogomolny equations, you can combine, well, they amount to 3 equations in this case, but you can combine them into one complex and one real. It's, I think, tons and totals. And the complex equation can be viewed as compatibility condition of 2 linear equations. So this you can think of as holomorphic derivative in x theta coordinate directions. And this is sort of corrected by the Higgs field monodromy operator around the phi direction. So indeed, as Jan already mentioned, to do this, we had to single out one of the 2 periodic directions, and we chose phi here. So then V will be exactly the monodromy operator around the phi direction of this corrected connection. Now, the other equation here tells us that this monodromy is essentially holomorphic in x phi direction. Because phi direction is periodic, well, let's say with period 2 pi r theta, it's convenient to introduce this new coordinate, which is coordinate in C star. And then basically these equations tell us that eigenvalues of V will depend holomorphically on S. So if you look at a spectral curve, if you look at characteristic polynomial of V of S, then it's clearly polynomial in T, and our boundary conditions are chosen in such a way that it follows that coefficients of these polynomials will be rational functions of S. So to make things a little simpler, let's find their common denominator multiplied by Q of S, so that the curve itself, the curve of eigenvalues of phi monodromy, is given by a polynomial. What we described on the last slide is exactly the Newton polygon of this polynomial. Now, as I mentioned, this required choosing one of the directions, but the resulting Newton polygon was defined only by the charges. So if you chose another direction, you will end up with exactly the same Newton polygon, maybe with different coefficients for the polynomial, but 2 polynomials will have the same Newton polygon. Second, the curve given by vanishing of this polynomial is the spectral curve. Why spectral? Because, well, it consists of eigenvalues of the monodromy operator. And this curve lives in C star cross C star because, well, these are eigenvalues of GLN matrix. Because of this curve of eigenvalues, it comes with its own eigensheaf. And if you look at the undecomposable situation, that is a situation where the monopole is not just direct sum of 2 different monopoles, then this eigensheaf is actually an eigenline bundle of the curve. So the statement is that this pair, the spectral curve, an eigenline bundle, and one also needs to keep track of parabolic structure at the points of infinity on this curve. It is equivalent to this. This is what we call phi spectral data, and phi spectral data is equivalent to the solution itself. We could have considered the same problem, but singling out the theta direction, and that would give us theta spectral data, because either of the two determines the solution in one-to-one correspondence of the solution. There should be a map between the two. However, this map is fairly transcendental. If you wish, this pair describes our modular space in terms of one complex structure, and this describes it in terms of an orthogonal complex structure. So if we knew this map, we would know right away the metric. So that map is not known, but this is a convenient algebraic geometric description of the modular space in one complex structure.
So, Sergey, this Qj plus minus, do they appear in the definition of parabolic structure, or how they enter? It looks like you need to choose a toric surface which compactifies your C star cross C star, and this race should be give a fan for the toric surface, or something like that.
Exactly. But the parabolic structure is rather to keep track of first position of Dirac singularities along the phi direction, and second, to keep the subleading terms in the monodrome. So
okay.
we need to keep in terms of our
case. All right.
Yes, that's right. So that description gives us a very nice description of the modular space, the total modular space. First, the parameters. The parameters are perimeter coefficients of the polynomial. That is, so every, I guess I didn't mention what Newton polygon is that you take a grid, and for every mn for which there is non-zero coefficient, you mark a point with coordinates m and n. Once you have all these points marked for a given polynomial, you take convex hull of these points, and that's the Newton polygon. So some of these coefficients will correspond to points which lie on the perimeter, and those have to be fixed to satisfy the asymptotic conditions. But the internal points can vary, and these will correspond to moduli. Next, this parabolic structure, if you like, specifies monodromes of flat connection on M phi around the punctures, and those are also fixed by this asymptotic data. Right? So, as Jan mentioned, the slope, so Newton polygon, is specified by Q's, but parabolic structure captures subleading terms M and chi. I'm sorry. The Newton polygon is specified by Q's. The perimeter coefficients are captured essentially by M, and positions on C star of Dirac singularities, and chi and positions along phi of Dirac singularities are captured by parabolic structure. So those we hold fixed, but then interior coefficients can vary, and the dimension of the modular space, real dimension of the modular space, is 4 times the number of this interior integer points in the interior of Newton polygon. Well, why 4? So 2 times that is just the number of interior coefficients of the polynomial that we can vary. And then the resulting curve has genus equal to the number of interior points. And that basically gives you the dimension of corresponding Jacobian. So as a result, you can view the space, the total space, as being phi, but over space of curves. Base is modular space of curves with fixed Newton polygon and fixed perimeter coefficients. And the fiber is the Jacobian of that curve. So next, as I mentioned, if you come from differential geometry side of the story and want to know, for example, all gravitational instantons, then the very first question to ask is, which of these modular spaces have dimension 4, the lowest possible dimension? Well, by our theorem, they're all given by Newton polygons which have only one interior point. There are many such Newton polygons. So first, on the lattice, there is natural action of SL to Z, and this action will transform Newton polygon with, let's say, one interior point to another Newton polygon with one interior point. So the question is, what does this SL to Z do to the metric on the modular space? So our statement with Richard Ward is that this SL to Z acts as an isometry on the modular space. The reason for this is that, well, the T transformation of SL to Z, tau going to tau plus 1, is given by a fairly simple operation. You take your monopole solution on a bundle E, and you tensor that bundle with a line bundle on which you consider the simplest charge 1 abelian solution. So as a result, you can take the monopole solution and always add to it something. Well, this is, let's say, UN monopole, and you can add something which lives purely in the trace U1 part. And so you add to phi x times identity and corresponding addition to connections. Because L2 variation, delta A and delta phi, reside only in non-trace part, the trace part is completely fixed by boundary conditions, this is an isometry. The S transformation of SL to Z is the non-transform. So as a result, we have this large group of SL to Z transformation. So we do not have to consider all Newton polygons. It's enough to consider the orbits on the SL to Z. Now, all polygons with one internal point up to SL to Z are given in this list. There is this lovely paper about exactly these polygons and number 12 by Poonen and Rodriguez Villegas. It's really a joy to read. So it appears that we have lots of spaces to play with. And the question again is, are some of them isometric? Well, at first look, this P is the number of points on the perimeter. And roughly speaking, this P counts the number of parameters that our space can have. Intuitively, these control the shape of our space, of the modular space. So from this point of view, it is plausible that some of the spaces with the same number of parameters might be isometric. To explore which of them are, we observe that there is yet another symmetry. If you have an abelian monowall, then its spectral curve, well, has this form. And so the degree of T was given by the rank of the group, so here it's degree 1, and T has to be some rational function. And given a non-abelian monopole, we can always add to it any abelian one we want, and this will not change the modular space, as I already argued, because the trace part cannot vary. It satisfies Bogomolny equation on its own, and it's abelian. And all the metric, all the L2 deformation is really in the SUN mod ZN part of the variation. So now, if you have a abelian monopole with this spectral curve, you can ask what happens with spectral curve A phi when you do this change. So if the spectral curve of A phi was given by G of ST equals 0, then the spectral curve of this new different solution will be given by this polynomial. So if you take into account all these changes and see what they do to Newton polygons, you end up with much shorter list. Basically, on each line of the previous picture, you will get isometries, except for one of them, which leave you two options. So the list is much shorter. You have, 7 spaces. And these 7 spaces, when you look at it and think of the spheric diagrams, they exactly correspond to Delpezzo surfaces, except with 2 of them missing. So now that we have these 7 spaces, we would like to study the asymptotic metric and their overall geometry. So one of convenient way of visualizing this, of thinking of what happens to the spectral curves, is in terms of amoebas, regular subdivisions of Newton polygons. So this story is nicely explained in a beautiful book by Gelfand, Kapranov, and Zlevinsky, which is one of the books I found very hard to put down. Once you start reading it, it's a beautiful story. I highly recommend it. So if you have a curve in C star cross C star, you can simply project it onto R cross R by taking logs of absolute values of S and T. The image of your curve is some shape like this, which is called the amoeba. The complement, the complement of this amoeba is separated into convex connected pieces. And there is yet another gadget which describes, gives slightly different meaning to the amoeba, the Rankine function. So in a sense, this taking log of absolute value is a way to have a real world view on this complex curve. And since we do that, we might as well take log of the polynomial which defines it, except that will also depend on the phases. So we average over the phases. That gives us a function. This function, as it turns out, well, it's called the Rankine function. If you compute the gradient of this function, then you can interpret right-hand side of the gradient as holomorphic integral. And this holomorphic integral, of course, if there is no pole inside, it doesn't depend on it. So the gradient of this function is constant outside of the amoeba. That means that outside of the amoeba, this function is the graph of this function is given by a plane. And that's another way of defining the amoeba. It's where a Rankine function is not linear. So outside of the amoeba, you get these planes. And moreover, every connected component of complement of the amoeba corresponds to a particular vertex of Newton polygon. This linear function will be given, well, the slope of that function is given by coordinates of the corresponding point, mn. So you get this linear graph, z equals to mx plus ny, plus subleading term, which is specified by the coefficient of the polynomial. If you start increasing these coefficients in the interior, then the amoeba will start shrinking toward what's called the amoeba spine. And the way to visualize this amoeba spine is just taking these planes, forgetting about the regions in between, and simply intersecting those planes. So projection of this nonlinearity on the two-dimensional plane will produce the amoeba spine. Intuitively, when we increase the moduli, the curve starts shrinking to the spine. And today, we'll describe in a minute what the curve looks like. So what happens to the actual monopole when we take this limit, when we allow moduli to grow? Well, this, if you think first in terms of the plane arrangement, so here we took the Newton polygon, we colored the vertices. For each vertex, there is a corresponding plane. The slope of the plane is given by the integer coordinates of the point. So the perimeter planes have the highest slope, and then there are other planes in between. And then it's these coefficients which we allow to vary. As we vary this coefficient, we move the corresponding plane up and down. Okay. So as a result, depending on the relative position of these planes, we will get a very different picture when we project down the corresponding planes. So it might look like this, might look like that. Now, each corresponding projection gives us a graph on the plane, and this graph is dual to some partition of the Newton polygon. And these partitions are called coherent or convex or regular partitions, depending on where you look in the literature. So if you like, you can take this as a definition. A regular partition here is the one which appears as dual to one of these plane arrangements. So as we found with my former student Rebecca Cross, there is a good physical interpretation to this picture. So once again, this two-dimensional picture is simply a projection of this three-dimensional picture into the horizontal plane. Namely, every vertex here of this picture, which corresponds to some triangle of this triangulation, is a monopole wall. So its x projection is a position of some monopole wall. And every region between these vertices is the space where your field is more or less, the magnetic field is more or less constant. Rebecca proved that this approximation of having the field just a billion between the walls is actually exponentially good in the distance to the closest wall. So now studying the dynamics of this wall, studying this metric on the modular space amounts to studying electromagnetic interaction between these walls, describing their motion, and from that extracting the asymptotic metric. When she did this calculation, she proved a surprising fact about the asymptotic metric. So before I state the fact, let me just recast the dictionary, which translates this geometry to physics. The Newton polygon encodes the charges of the monowall. Each regular triangulation corresponds to a monopole wall splitting into subwalls. Just as if you take an atom, you can split it, except if you split an atom, every atom splits into its elementary constituents, always the same way. But if you take a monopole wall, it might split into elementary subwalls in different way, depending on how you changed your moduli. Each such splitting corresponds to some triangulation. Now, every edge corresponds to some U1 factor of the monopole interaction. And the secondary cone of this, which I'm going to describe in a second, corresponds to a phase, or it tells us in which constituents the monowall splits.
Okay, may I ask you, is there a dictionary between geometry and algebraic geometry? Similar one. I mean, you consider, you have this moduli space of spectral curves, yeah, and for each spectral curve, you consider kind of, like by analogy with usual Higgs, you consider a pure dimension one coherent shifts with support on this spectral curve. So the whole thing can be, it looks like it can be described pure algebra geometrically. And then like you can see your SL2 Z action and your
Yes.
decomposition should correspond to some decomposition of this moduli space. So
well, so this decomposition, it manifests itself asymptotically. If you like, in terms of the curve, it corresponds to degeneration of the curve. It's infinity. And how your curve degenerates at infinity depends on how you manipulated your moduli, your parameters.
But can I kind of make this analogy with the usual Hitchin system? So my spectral curve can degenerate, so I go to the discriminant, and you describe the structure of this discriminant and combinant. Okay.
Exactly. So if you like, this is tropical manifestation of the discriminant.
Okay.
Except in this case, this discriminant is not written. There should be discriminant there. There's a good algebraic problem. But let me come to this in a second when I describe the secondary data, secondary fan, secondary polynomial. So please ignore all the formulas here, especially if you're not a physicist. Let me just describe how Rebecca computes the asymptotic metric. Given monopole wall, she proved that away from the core of the wall, so away from any of these points, the Higgs field behaves linearly up to exponential correction, exponential in distance to the wall. So every wall you can think of outside of some region right next to the wall, it just has linear Higgs field in each component. So your UN structure group is split into U1 to the N, and each U1 component behaves this way. Q is the charge of your wall with respect to that U1. So next, we're interested in how two walls interact. If we change moduli of one wall, well, we can allow this wall to fly in the x direction. That's very easy. You take this solution and perform the Lorentz transformation. It can also move in any of the periodic directions. So magnetic charge moving, magnetic wall moving in any of these directions will produce electric field perpendicular to it. And also there is another phase, magnetic phase of this wall. And if you allow it to roll along the magnetic field, magnetic phase, and it produces the electric field. So in the end, it just amounts to classical electromagnetic problem of walls with electric and magnetic charge interacting. So once you map all our moduli to this, then it's fairly straightforward. It's standard procedure, writing out induced potential, Lenard-Wishart potentials. And then once you have this, if you're interested in ith wall, you sum up potentials produced by all other walls, and you write the Lagrangian for the ith wall, and you sum them up. When you're done all this and you presume that all velocities are small, then your Lagrangian looks like a particle rolling on some space, and you can read off the metric on the space from these coefficients. And this is exactly the asymptotic hyperkahler metric on our space. But again, this is valid only when our monopole wall is separated into elementary pieces, and these pieces are far from each other. So it gives you the asymptotic metric, but only in the directions which are far away from the discriminant that Jan mentioned. So moreover, this metric can be packaged into its scalar potential, which is given in terms of a single function. And this function is actually, it's Legendre transform of the scalar potential, if you wish. And it has this form which is expressed in terms of basically properties or the slopes of the triangles which appeared in your triangulation. That's what these G's are. Now here is the result that Rebecca proved. Is that the scalar potential of this asymptotic metric is given in terms of this function, and this function has good geometric interpretation. Let's look at this plane arrangement that I described. There are planes which correspond to perimeter coefficients of Newton polygon, and there are interior planes. The perimeter planes are fixed by the boundary conditions, and the interior planes can move up and down as we vary modular. Let's look at perimeter planes alone. And let's look at a set of points above all planes. This forms what I'll call a crystal. Now we can look at all points which are above all planes, perimeter or interior planes. And that's what I'll call a cut crystal. So what Rebecca proved is that the Kähler potential is given in terms of a function that is equal to the cut crystal, that is the difference between these two. So look at points which are in the crystal but not in the cut crystal. So the Kähler potential of the asymptotic metric is equal to generalized Legendre transform of the cut volume. So that gives a handle on the generic directions, asymptotic directions in the moduli space. Now I would like to describe the structure of the space itself. Given the Newton polygon, there is a notion of secondary polyhedron, and it's obtained by this GKZ prescription. That is, take your vertices and number them 1, 2, 3, 4, 5, so forth. Then look at any regular subdivision. The point is that every regular subdivision will give you a vector in n-dimensional space where n is the number of points. The prescription is this: take, let's say, first point. To find out the first coordinate of that vector, ask yourself, what is the area of all triangles for which it is a vertex? So in this case, the area is 5. Now ask the same question about the second one. Well, the area of this is 1. Just to avoid any ambiguity, in this convention, the area of the basic simplex is 2. This way you, is 1, not 1/2. This way we avoid lots of 1/2s and starting. Okay, so given a triangulation, you immediately have the 6-dimensional vector in this case. And these vectors form vertices of a convex polyhedron, which is called secondary polyhedron. So in this case, the secondary polyhedron looks something like this. Now we can draw normals to each face, and two normals are connected if the faces are adjacent. This way, you will get a secondary fan, which is dual to secondary polyhedron. This encodes nicely both the parameter space and the moduli space in the following way. Secondary polyhedron has an associahedral face that involves only triangulations which involve only perimeter points. That's the largest face of it. Now you can look at subspaces which are orthogonal to this face. So let's look at the secondary fan and project it down onto that face. That will give us the face structure of the parameter space. That is, as you remember, it's the perimeter coefficients which are parameters in the problem. And varying the internal coefficients moves us up and down in this space. So this projection tells us what kind of transitions this moduli space can have. Any point here specifies the parameters, fixes the geometry of the space. As you vary those parameters, the geometry space, or even topology of the space, might change as you go through this resulting walls. So indeed, the discriminant, or if you like, this sort of secondary fan, is the tropical degeneration of this discriminant. There is discriminant here. But now what is needed is another object. Once you fix the perimeter points, there is another notion of discriminant which describes the moduli space itself. So if you like, when you fix this point, you look at the space, you move up and down, and you can intersect that with the fan. And that gives you the structure of the moduli space. Now to quickly wrap this up, there is, well, this is a sort of standard tropical story that our usual addition and multiplication are really quantum operations, according to Maslov.
I'm sorry, can I interrupt a bit? Sorry.
Yes.
So I have a question about your previous pictures. You show the up and down. What do you mean by up and down? Is there a projection involved?
Yes. So let's look at the secondary polyhedron. Secondary polyhedron has an associahedral phase. It is a phase which involves only triangulation. Its vertices are only triangulation, which involve only perimeter points. That defines a subspace. So we can take a fan and project it on that space. That will induce a fan of lower dimensions. And that tells us about parameters. And now, if you fix those, what lies above each of those points is sort of tropical version of the moduli space.
Okay, I got it. Thank you. That's all my question.
Okay. So, given the time, let me simply state what compactification is. So, to sort out the compactification, we have to understand what happens to this whole picture when the curve in C star cross C star becomes very large. If you move in these generic directions that I described so far, then the curve decomposes into narrow tubes connected by 3 punctured spheres. A wonderful way of capturing this degeneration is using hyperfields that I learned from Oleg Virov's paper. And it involves this very strange operation. If you have 2 complex numbers, and if you want to add them up, well, if you multiply them, you just multiply. That's not modified. But if you want to add them up, the result is not, well, it's not a field, it's a hyperfield. The result is not a number, but a set. So if one number is larger than the other, if A is absolute value of A is larger than B, then it's A. The answer is A. If it's the other way, then it's B. But if the 2 of them are opposite, then the answer is this whole disk. And if they're not opposite but have the same absolute value, then it's an arc connecting A and B. Okay, let's for a second play a game and construct, let's say, what is solution of t plus s plus 1 equals 0 means. All right, so first we need to construct s plus 1. That in general will be a set. Then we add t to that, which means that for every member of a set, we add t to that, and that will be another set. It's the union of this. And this equation means that the resulting set contains 0. Okay, so first let's solve, let's write what s plus 1 is. Well, if s is greater than 1, then s wins, it's s. If s is, absolute value of s is less than 1, then 1. If s is minus 1, then the answer is a disk like this. And if absolute value of s is 1, and this is not minus 1, then it's an arc connecting 1 and s. Okay, is this readable?
Yeah.
So now we're going to add t to this and see what this means. Right? You want to visualize this on the plane with ln s and ln t. And basically what we just found is that for on this real line, oops, I guess it's lost forever. So for s for S outside the unit circle, S plus 1 was really S. The only way for T to have S plus T to have 0 in it is if S plus T is a whole disk. So if T is minus S. It gives you a line here. And in terms of the phases, argument of S and argument of T, they're shifted by pi. So it looks like this. For S negative, S plus 1 was 1. So the only way for 1 to be in set S plus T plus 1 is if T is minus 1. Okay, so you get a line like this. And in terms of the torus given by the arguments of S and T, it's given by this. Argument of T is pi, and argument of S can vary any way it wishes. Next, if S was minus 1, then there was a whole disk. So T can be anywhere within this disk. And that means that you have this line, and in terms of the torus, you have this line. And then the only case that remains, so far what we obtained are the 3 tubes like this, like that, and like that. And now if you want to understand the adjuncture, then this is the case where we looked at S plus 1, and that was the arc connecting 1 and S. So that means that T has to be in the antipodal arc, opposite to it. So T has also to have absolute value 1. That's at the origin. And in terms of this phases, it means that the phase of T can be anywhere between 0 and phase of S. So it will be this kind of intervals. So you can see that the blue line is glued in here, the purple circle is glued in here, and the other one is glued in there. So the asymptotic degeneration of the curve is captured nicely by this hyperfield, where these 3 cylinders are glued by this shape with kind of 2 triangles glued to each other like this. However, this is a nice story capturing this maximal degeneration, but it doesn't capture the mixture of degenerations. If some of the monopoles don't separate, but we look at asymptotics where some of them move in a cluster and the other bunch moves in a cluster, then what will be captured here is some Riemann surface of higher genus, not necessarily a sphere with 3 punctures. So you need some entirely different story to capture this. And just to finish the story, we'll say what this is. This is this exploded geometry of Brett Parker, which is a beautiful way of combining tropical and complex geometry at the same time. So it can keep track of pieces of the curve which separate and pieces of the curve which remain. And the result of this is that we have very good view now of what the right compactification is. So you should construct given the polygon, construct a secondary polytope, look at its dual. And then what you have to do is, so with hyperfields, you can glue hyperfield curves on surfaces, but there is a lot of geometry happening on the junctures, and that is captured by instead beveled polygon, where you chop off the vertices of the resulting polygon, and then you take the edges and shave them off with a planer. So each of these beveled surfaces now has corresponding exploded geometry of Brett Parker, and the whole space can be understood as one exploded space. And as a result, there's indeed nice algebraic geometric description of the base of the moduli space. Okay, so to conclude, doubly periodic monopoles are interesting for various reasons, either for people studying quantum field theory, brane dynamics, or gravitational instantons. The decorated Newton polygon captures the boundary conditions and all the moduli. And a secondary fan gives the phase structure of the parameter space and description of asymptotics of the moduli space. Now, almost all self-dual gravitational instantons are moduli spaces of monopoles or instantons. And those that I don't describe today also appear if you allow high charge Dirac singularities. The asymptotic metric, asymptotic Keller potential, is given in terms of the cut volume of the plane arrangement. And exploding geometry gives a very nice description of the compactified moduli space. Again, this will not be usual compactified variety. It's this exploding manifold sense which delivers the right answer. So I'll stop here.
Thank you very much. Very nice, complete picture. Questions, please?
Yeah, I had a question.
Yeah, Gabe.
Could you, this beveled secondary polytope, is there a, could you describe, so you said you're sort of truncating the secondary polytope, is this, or is there a more geometric way of seeing what the faces correspond to relative to the triangulations or subdivisions?
Yes, that's right. So triangulations gave us vertices of secondary polytope, but there were other subdivisions, not necessarily triangulations. For example, if you look at let's say these two, they're related by a flop, by a flop using this edge. So let's erase this edge. That will correspond to this shaved off edge between the two. So in the beveled version, every face is given by some regular subdivision. And any partial subdivision, which is not triangulation, corresponds to exactly this direction in which some of the monowalls are actually clustered together as you go to infinity. Or in terms of the spectral curve, it corresponds to degeneration of the curve, where tropical degeneration doesn't capture the whole story. And some of these pieces of, so the curve essentially becomes very large, but its pieces have higher genera.
When you said every face, you mean every facet. You make everything.
Every facet. That's so every facet corresponds to some subdivision, and if you like, they're sort of partially ordered depending on how far they are from being triangulation.
I see. Thank you.
More questions?
Yeah, can I ask a question?
Sure. Good.
Yeah. So this is a physics kind of question. So you mentioned that these doubly periodic monopole moduli spaces are related to Coulomb branches of five-dimensional theories with n equal 1 supersymmetry on a torus times R3. And so I wanted to ask if you could say some words about what happens when you take one of the circles to zero size. So how does this, whether this approach is something like a deformation of a Hitchin system, how does that work? So for example, there's a case that was worked out by Nekrasov where one gets a relativistic total system, but I was wondering if there's a more general story here. And the second part of the question is regarding the asymptotic metric that you wrote down at some point. So whether in this four-dimensional limit, this approach is what people call the semi-flat metric of the Hitchin system.
Yes, so the relation with Hitchin system is really fascinating here. In my mind, doubly periodic monopole plays the role of a Hitchin system with group-valued Higgs field. So when you consider Hitchin system and Higgs description, when you take characteristic, well, the spectral curve there, that's eigenvalues of phi. And the role of phi here is now played by holonomy. So in the Higgs view, this is exactly Hitchin system, but with group-valued Higgs field. You substituted phi, which was an endomorphism, by the holonomy. Next, you can track the degeneration. And what surprised me is that this picture that I was describing today with the secondary polyhedron and the sort of structure, it appears only for doubly periodic monopoles. I used very heavily the fact that spectral curve lives in C star cross C star. When you degenerate to Hitchin system, this picture gets squashed, it disappears. Because the curve, if you like, turns from curve in C star cross C star to curve in C cross C star. Nevertheless, there is relation between integrable systems or between gauge theories. We can take 5-dimensional gauge theory on a torus and then take a limit of it as one of the circles of the torus goes to 0. And this will recover the 4-dimensional gauge theory. And also moduli space will change correspondingly and limit to the corresponding other space. So on the level of the integrable systems, on the level of gauge theories, there is a correspondence. But unfortunately, this picture that I was describing today will disappear. I guess another way of formulating this is that in 4 dimensions, in a sense, the equations we study, monopole equations or Hitchin equations, they come as reductions of self-duality equations in 4 dimensions. Those equations were conformally invariant. And Hitchin used it to put Hitchin system on a curve, for example. However, if you look at periodic monopoles, for example, then it's very hard to take advantage of that conformal invariance because this conformal transformation does not respect the logarithmic boundary conditions for the asymptotic Higgs field. For doubly periodic monopoles, there is a rescaling which takes advantage of this conformal symmetry, and it respects this linear behavior, linear asymptotic behavior.
Pietro, are you happy with the answer?
Yes, thank you very much. I was also just curious about the statement about the asymptotic metric, whether,
Right.
yeah, so what happens between the degeneration limit, if you can say just a few words about that.
Yes, so, oh yes, then that's, I guess, my chance of answering this question together with Jan's question about the metrics. That, right, so there are all these sort of metrics which are distinguished by how fast the volume grows at infinity. So today I focused on this ALH metrics, and I described them in terms of monopole walls. And as Jan mentioned, there is also this triply periodic monopole, which gives the essentially half K3 metric. Now what you can start doing, you can start varying the size of one of the circles. For example, opening up the circle of the monopole. And then each of the spaces will have the corresponding limit as an ALG space, a space of periodic monopoles. And those in turn, again, can limit to ALF spaces when you open another circle. However, when you take a limit, you have to be careful because not only you're changing the geometry of the space, but also you need to decide where in the space you're standing. So your space, let's say, becomes large, maybe some cycles in that space become large. And as a result, topology in the limit will change. So few of ALH spaces might limit to the same ALG space, for example. or if you're not careful, your space might become too simple. It can become like R3 crosses 1. So indeed, on all these spaces, there is a structure of one of which can appear as limit of which.
Is there a 6D theory which is related to triple periodic?
Not that I know. No, 6D theory is related to Z2 equivariant instantons.
Okay, so so Pietro, are you satisfied with that answer?
Yes, yes. Thanks a lot.
Yeah. More questions? Yeah, actually, I have kind of a question in this your story with spectral curves and C star square and this rational slopes is QJ. I mean, it's a similar geometry not only for this group valued Higgs, but also for Q difference equations on C star. But I didn't see any Q. I mean, in your talk.
Yes, it's a finite time constraint.
So you have sub-talk for every slide of your. All right.
Yes, so indeed, all these are related to Penlevé equations, some continuous and some discrete. These appear if you study periodic monopoles, and these appear if you study doubly periodic monopoles. So each one here has a corresponding Penlevé equation.
No, but
just as I
I'm
mentioned,
confused.
some of them.
Penlevé should be, I mean, by analogy with ordinary, it should be kind of non-linear equation which describes sort of isomonodromy or isostocks probably in your case because it has these directions. But for what? Does these Q difference equations have any meaning in your?
Right. So well, I'm very curious about these questions. So every discrete Penlevé equation, for example, is a certain move on elliptically fibered surface. So it starts with maps of P2, but then you have to blow it up so that it satisfies the integrability condition. And these are exactly in one-to-one match to the surfaces that I was describing today. The question that I'm asking is, what does this map do to corresponding monopoles? So instead of mapping the surface or mapping asymptotic conditions, under discrete Penlevé, the surface essentially maps to isomorphic one. So instead of mapping one surface to another, you can say that you fix the surface, but you do something to the points on it. So my question is, what does that map do to corresponding monopoles? And is there physical meaning to this map? And once you answer this question, you would know what it does to corresponding gauge theories. But I don't know the answer at the moment.
And still, I mean, I asked it several times in different versions, either algebra geometric description of these moduli spaces, so that like your discrete symmetries are just autoequivalences, for example, of or equivalences if you consider different moduli of certain categories of coherent sheaves. So, I mean, it just probably the reference question. Did anybody?
Well, the original papers on Penlevé and discrete Penlevé, they all discuss so like Sakai and
No. I
Naomi
mean monopoles. Yes, yeah, I understand, but it's kind of abstract theory. Yeah, there was also.
Well, but we directly relate to that abstract theory. right? Once we reduce to a curve and the bundle on it, that's it. So in a sense, we're studying universal Jacobian over a family, particular family of curves.
Mm-hmm.
And these families happen to coincide exactly with those families.
Mm. Okay. Okay.
And
Yeah.
what's the meaning of that transformation that you mentioned in terms of monopoles? I do not know, but it's very likely that it's meaningful.
Okay. More questions?
The D or this is. So one of them, the E4 is you regard it as the same as A4, right? Not the D4. I assume these are some sort of Dinkin diagrams. Yeah.
E4, D4.
Uh-huh.
Yes, so.
And the E5
right,
so, is supposed to be the same as a D5. Oh, that's right, yeah, as you point out.
Yes, yes. So unfortunately, in this business, there are many different labels. So for me, depending on which series I put it in, D or E series, is determined by not just by Dinkin diagram, but by the geometry of the space. For example,
I see.
For me, there is meaning to D3 as opposed to A3, even though Dinkin diagrams are, of course, exactly the same. But my asymptotic geometry is quite different. So if you look at a group, well, even for D4, so if you look at, let's say, Z2 cross Z2, then group theory, there's no distinction, but it's important for me how it acts, for example, on complex structure.
Okay.
And that's where the difference is hidden. So it's geometry which knows the difference between the two. But indeed, depending which paper you pick, you have very different labels here and different notation, even in the classical literature.
Sergey, may I ask, I also forgot, you mentioned that this moduli space, they somehow even isometric to the moduli spaces. No, it's only for R3, arising in 3D and equal 4. Yeah. So it's not what you were talking about. Yeah, it's just ordinary monopoles in R3. Yeah, without periodicity. All right. Okay. No, my question is dismissed. So last chance to ask Sergey a question.
Let me ask, take this chance. So in the very beginning, you have this R for R3, the monopole. You have the D3 and N equals 4. But when you have the next one, the N dropped by 2. So why that dropped by 2? Yes, here.
Why
so
this is N equal 2 and this is N equal 4?
Yeah.
Oh, it's really peculiar the way physicists count supersymmetries. So they all have 8 real parameters. But the way physicists count is that they pack the supersymmetry transformation parameter, epsilon, into a spinner. And then they count how many spinners you need to specify the transformation. So in N equal 5, exactly, it's just the number of spinners. So if you simply count real parameters, there's 8 real parameters in each situation, just the way they are packed into spinners.
I see. Okay, thank you very much.
Okay, still one more chance.
You don't have an end.
Yeah, I mean, it's never-ending story. Okay, if there are no questions, so thank you very much, Sergey, for a wonderful talk.
Thank you.
And this is it. So.